Well, thanks everybody. I know it's summer. Hope your summer's going well. Just a kind of a brief little introduction to 5G here. And I want to talk a little bit about the uses, the technology, something called slicing. Maybe you've heard of some of the term slicing before, how it's going to be deployed, and some of the different configurations and projects that are going on with 5G. This is kind of an evolution. Some of you are probably don't remember the 1980s, but I certainly do with the first phones. You get about 10 years out of these technologies. And the reason why is they got to get a return, an ROI, the providers. And it's about 10 years, if you look. The life cycle of this stuff is 10 years. And it's not so much the technology that's driving that life cycle. They're looking for a return on their investment in the antennas and the devices that are being built. So this has been a rollout. 80s, we started with 1G with the old giant phones. And here we are today. I'm moving in the direction of 5G. So this is a slide here that shows, what we're looking at for data. Average internet use, these are projections for 5G, 1.5 gig per day. That's an individual. Autonomous vehicles, huge. 4 gigabytes up to a terabyte. Connected planes, 5 gigabytes per day per plane. Factories, 1 petabyte per day, and cloud video providers, 750 petabytes per day. So we're going to see a massive increase in bandwidth as 5G rolls out. This is just a quick slide showing comparisons, comparing 3G, 4G, and 5G. If you look at how long would it take to download 2-hour-long Guardians of the Galaxy, 26 hours on 3G. 6 minutes on 4G, that's pretty good, right? That's kind of where we are right now. 3.6 seconds with 5G. So you're seeing massive, again, just massive increases in bandwidth. And it really makes people start thinking, what can we do with all this bandwidth? So let's talk a little bit about some use cases now. This is one that I'm most excited with. I've done a lot of work since 1995 up in the Northeast with the company that's now Verizon. Landline especially, you're going to see this fixed wireless access replace copper wires. And if you look, Verizon has sold off a lot of their Fios, their fiber to the prem or fiber to the home territory. Frontier is probably one of the bigger ones now that's picked up a lot of that. Frontier's having some financial problems right now. So you're going to see that last mile, which is what the telcos refer to this as wireless with 5G. So, and there's different configurations. I'll talk a little bit about the different configurations with stuff, but it's very interesting. 15 years ago, fiber to the home was the big thing. The original Ivan Seidenberg, the original CEO, or the old CEO of Verizon, kind of bet the farm on that project. $15 billion, I think, Verizon put into building that network, and they've sold quite a bit off already. And they're moving, full speed right into 5G. So there's all kinds of different markets and use cases. Smart cities, agriculture, homes, industry. These are just a few of the things that are coming down the pike here. Remote surgery with haptic feedback, full self-driving. I'll talk a little bit about that and some of the stuff Tesla's doing now. Some of the online gaming, all kinds of robotics. So we're heading into some pretty exciting and pretty interesting times. Holograms is another one. So some of the different use cases, and these are interesting. This comes from the 5G Americas project. Extreme mobile broadband. Okay, you get human to human, human to machine, and machine to machine stuff going on right now. Massive scale communications, ultra reliable, low latency services. Latency is very important, especially when you're talking about something like vehicle-to-vehicle communications, for example. So again, these are some of the acronyms. There's a ton of acronyms, and these are some of the things you'll probably run into if you do a little reading as you get into some of this content a little deeper. Now, let's talk a little bit about the technology now. this is kind of where we are right now. This is a little very busy diagram. We've got all these separate networks set up right now. Let's just look at 4G, for example. You've got this 4G network that's set up right now, and it's connected into the voice network. It's connected into the internet. There needs to be interfaces. Very complicated. There's a lot of separate pieces of equipment that are required. And how do you tie a wireless network, a 4G voice network, for example, into the public switch telephone network? Still a lot of people still do have landline telephones in their homes. So there's different interfaces. Over here on the right, you can see some of the different acronyms here. If you do some searching on those, you'll see you'll find that a lot of that is interface type gear equipment that they're using. A lot of this is going to go away now. So this is where we are right now. Okay, so this is kind of where we're going. Well, this is not kind of, this is where we're going. There's going to be new antennas, new network architecture. So you're going to find one network for home connectivity, cellular connectivity. Satellite is going to be integrated into some of this. And again, I'm going to go kind of quick through some of these things to give you an idea of some of where this stuff is going. Again, what it'll bring, it's going to be a more efficient network. You look at what the telephone companies, the old telcos, I keep using Verizon as an example because I have a lot of experience with them. They're really not hiring a lot of people right now. A lot of their central offices used to be, they all used to be full of, pretty large pieces of hardware, doing all kinds of switching and those kinds of things. A lot of those central offices now, the floors are empty. They've been replaced by, single pieces of equipment. So this whole 5G is going to bring a whole another level of this simplicity and efficiency to this network right now. Talking 20 gigabits per second, lots of traffic capacity. It's very highly efficient with regards to energy. So, energy costs, fuel costs will be down. High density as far as connectivity goes. Very, very low latency, along with 500 kilometers per hour connectivity. So here we are talking about cars again, where you've got vehicle to vehicle and vehicle to stoplight or other traffic control devices. It's very important to have low latency and high speed access. Much more spectrum efficiency, so they can cram more information, more data, more voice, more video, whatever the heck it is, into the same amount of space with regards to spectrum. And just huge user experience data rates. So we're seeing it's really a revolutionary product, a revolutionary time with this stuff. So a little bit of spectrum, and I don't want to go too deep into this, but the focus is on radio wave. Obviously, it's wireless, and this kind of gives you. This is just a sort of a broad spectrum diagram. Starting with AM radio and run them right up to radar and those kinds of things. So, but that red line, that radio wave spectrum, is where this is broken out. This is what we want to look at. And if you look at the way the spectrum is going to be used, okay, there's something called LTE Advanced, 5G LTE, whatever you want to call it. That's what my phone says I have. 5G below 6 gigahertz, kind of where that is. Then you get into what they call centimeter wave stuff, between 6 gigahertz and 20 gigahertz. And then you get into the millimeter waveguide stuff, which is very, very high frequency, very fast. One of the things, lower frequencies have a wider wavelength, and longer wavelength signals will travel much easier through like cement walls. They'll travel over large distances. You get up into the higher frequency stuff, the wavelengths are shorter, so they get more bandwidth out of a high frequency, but they don't get the penetration and they don't get the distance. So you're going to see a mix of 5G, low frequency, in maybe the 6 gigahertz to 20 gigahertz range. And then you get up into the millimeter wave stuff. And again, I'll talk a little bit more about this and how this is all going to work in some coming slides. So the millimeter wave stuff, the antennas need to be much closer together because the signals just don't travel as far. The antennas themselves are directional with 5G. So with 4G, you can see here this diagram. You can see you've got sort of these circles, the circumferences or radiuses that an antenna will cover. And the 5G antennas are directional, and they're much more efficient by doing it this way without getting into a lot of, well, some of the antenna technology. You can look at the evolution of an antenna. They've shifted to this single antenna, you know, in the 90s, back in those early days of wireless, passive antennas to active antennas, where you get, they're called MIMO antennas, multiple input, multiple output antennas. I'll talk a little bit more about these in a little bit on a slide coming up. But they're much more efficient, and they can operate at much higher speed. The smartphones today, let's talk a little bit about this millimeter wave stuff. If you look at your smartphone today, pretty narrow frequency range between 3 kilohertz or 3 kilohertz and 3 gigahertz is kind of where these things run. And we're seeing a lot of congestion now in that frequency space. But the shift now is to use frequencies into that millimeter wave range. Frequency you're seeing, again, you're going to see shift of frequency between 30 and 300 gigahertz. Right now, you don't have anything. At least there's not mobile devices transmitting in that frequency range. But by moving up into those higher frequencies, there's sufficient bandwidth. There's enough bandwidth for this Internet of Things that people are talking about. The disadvantage, though, again, as you get up into the higher frequencies, is signals don't travel as far. You know, they don't penetrate stone walls. You get trees in the way. You get some heavy rain or snow. It can cause problems with signals. So as far as massive MIMO goes, this multiple input, multiple output antennas, they're already doing this. It's not quite massive yet with LTE. LTE, I think they're doing up to around 8 antenna elements. 5G, they're talking several hundred antennas at a receiver transmitter station. It requires something called beamforming. I'll talk a little bit about that. I think that's on the next slide. But these MIMO antennas require beamforming, again, without going into a lot of detail. But what they do is they'll send signals and they'll stagger the intervals using several different antennas. You know, these MIMOs, again, have got hundreds of antennas built into the towers. And what these transmitters do is they target the location, the approximate location of the client, and they basically line it up. They line transmission power accordingly. And what they do is they create it. It's like a beam, like a tractor beam on Star Trek, maybe is a good way to think of it. So what they end up doing is they end up sending individual signals to individual recipients in different directions. And by doing that, it increases the coverage. It gives a much more stable connection, and they can go at much higher transmission rates. And they can also avoid some of the interference caused by, I think they're like a laser beam, maybe. Maybe that'd be a good way to think of it. You know, it's directly connected, but wirelessly. So we're shifting from silos to a common core. And again, this before here, kind of got the mobile core. We got a fixed network, which is the public switch telephone network, or maybe the cable TV system also delivering that. We got private networks, and we've got an IoT network. So what we're seeing with 5G we're seeing this shift to a 5G core with everything operating or connecting into that single core. Much, much simpler, again, much more efficient and much faster. The other thing I wanted to mention quickly, we're seeing semiconductor solutions with regards to data security. I know a lot of you are teaching data security, and we're starting to see at the silicon level, security being integrated or built into the semiconductors themselves. And we're seeing this with the Teslas now. If you follow Tesla in their full self-driving option, if you have a Tesla, if you know somebody that does, I think it's $8,000. They just bumped up the price. If you have an older Tesla, you have to upgrade from hardware 2 to hardware 3, and there's a bunch of reasons why. One of the reasons why is because they've actually integrated some security, built in some security right into that hardware. I'd love to talk about Tesla sometime, if anybody's interested. This is just a really busy diagram, but basically there's a control plane and there's a user plane. Sort of like the way the public switch telephone network works with something called SS7 now, Signaling System 7. Basically, you've got a lot of the control stuff going back and forth, and that's done for security reasons. And then you've got the communications plane. If you think of how a call is connected, it's connected. If you pick up your phone in your house and you dial a number, it actually makes the connection, the numbers processed through this separate control channel. And then you start talking, you're actually using user plane. So that's how this network architecture is set up the same way with 5G, the control plane and the user plane. They're slicing this network up using multiplexing. We don't need to go into it now, but I'd love to talk to, if you want, I could do some separate lectures even if you wanted on this stuff. But there's a slice here I'm showing for smartphones, there's a slice for autonomous driving, and there's a slice for massive IoT. Autonomous driving, you want it to happen pretty quick if you have a self-driving car. So you want that slice to be pretty fast with low latency, as an example. And here's an example of that right here. 3 slices, 1 card, 1 SIM card, 3 slices. 1 for the car sensors, cameras, radar, LiDAR, those kinds of things. 1 for entertainment in the back seat, and 1 for autonomous driving. And that autonomous driving slice, you want to be highly reliable, low latency to prevent collisions. So there's a bunch of different acronyms down at the bottom too. This stuff is full of acronyms. As far as the deployment model goes, this is kind of where we are right now. We've got 4G network. We've got phones now that, with both 4G and 5G functionality, and you've got 5G phone future, I guess. If you look at what T-Mobile has done today, this is their network. They did merge with Sprint, and that just happened, I think, in April. Sprint was actually discontinued 5 days ago, so they don't exist anymore. They become T-Mobile. So you're seeing this shift, and they currently offer 5 phones. I think one of these phones, only one of them has support for the millimeter wave bands, the higher frequency millimeter wave bands. The configurations and projects, okay, this small cell idea. They form a small network. You're going to see small cell used for small antennas used for, again, the autonomous driving piece. They're talking maybe every 150 feet, there'll be a small antenna on the highway. And these will be operating, these small cells typically will be operating at those higher frequencies, those millimeter wave frequencies. So very fast, but with very low latency. But because the frequencies are so high, that means the wavelengths are much smaller. They don't travel long distances. They don't travel well through objects. Now, I just want to finish this up talking a little bit about satellites, because there's a lot of really cool stuff going on with satellites right now. This could evolve to 5G. It is. It's going to integrate into 5G. You're seeing these, what they call mega constellation satellite networks going up, these low Earth orbit satellites. because they're low Earth orbit, they require, they be much closer to the Earth than the ones that are way up there. And there's all kinds of regulatory approval going on right now. There's at least 10 companies. Facebook is putting up their network. Amazon just announced about 5 or 6 days ago. It's called the Kuiper satellite network, 3,236 satellites they want to launch. So it's happening. These low Earth orbit satellites are happening. You've heard of the Iridium network. It was developed in the early 90s by Motorola. I think they spent about $11 billion on it. They lost their shirts on it. There's a really good book called Eccentric Orbits, if you want to read something interesting, by a guy named John Bloom. It's about Dan Closey. Motorola was going to actually let this Iridium network, let these satellites deorbit and burn up on entry. They were just going to let the network go. And this guy, Don Closey, came along and saved it. It's a very interesting read. Low Earth orbit, about 780 kilometers. They do get multiple coverage. There's 75 satellites right now with Iridium. There's 66 that operate, and they have some spares up there. Now, the one that I'm most excited about is Elon Musk's Starlink. They've been launching. I think they launch about 60 satellites per launch. They just launched one a couple of weeks ago. They've been doing this since May 2019. About 550 kilometers from the Earth. 42,000 Starlink satellites they're talking about. They're looking at gigabit internet speeds, latency in terms of milliseconds, very fast response, just like ground-based broadband connection, basically. You don't get that satellite delay in a voice conversation, for example. As long as Musk claims, as long as you have a view of the sky, you'll be able to get a connection. So they're going to see this the satellite stuff integrated, I think, pretty nicely into 5G. It's just another technology that's going to be accessing that core network. Then I might follow. Here's my email address and my phone number. I've got some resources too here that you can follow. There's a lot of concern about 5G and safety, 5G technology, telecommunication science safety. You can take a look at some of that stuff. A lot of students will ask you questions about those things. But here's my contact info. I am back teaching in the fall. I'm online. And I'd be happy to, if any of you are interested, having a guest lecture or somebody like that come in remotely, I'd be happy to do that sometime.